Hello, my name is Mahboob Khan, and our group project is about the Doppler effect. My group partners are Magalhaes and Mahboob. And right now, we will show you a brief video about the Doppler effects.
The Doppler Effect. In Sheldon's words,
it's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
the Doppler effect is perhaps best explained visually. So here's a thing that is emitting waves. It could be a fire truck emitting sound, it could be a star emitting light, it could be a duck creating ripples on a pond. Those are all waves, and they all look something like this. We see the Doppler effect happening when the thing that is emitting waves moves. In the direction it's moving, the wavefronts bunch up, and behind it they spread out. If our object is moving towards a stationary observer, these bunched up waves are observed at a high frequency, and if the object is moving away from a stationary observer, the waves are observed at a lower frequency. So that is the Doppler effect, the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer. It makes sense, but it gets interesting when you consider some of its applications.
I would like to talk about the brief history of the Doppler effect, who created the Doppler effect, and by whom it was tested, and the theory was finally proven. The Doppler effect is the change in frequency or wavelength of a wave for an observer moving relative to its source. Whee! It was created by the Austrian physicist Christopher Doppler in Prague, and he created the theory to explain the binary stars in 1842. It was first tested by Christoph Ballet in 1843 using 15 trumpeters with precisely tuned instruments to play on a train as it passed by the musicians while they were playing music, and it was proven when they heard the train pass by and there was a brief change in the frequency or sound. That was when Christopher Doppler's theory was proven. The three main factors are motion, wave, and frequency. I will be talking about the motion part. Hongvu will be talking about waves and frequencies, and Michael, he will be talking about how to apply it in the real world. Now, motion. What we mean by motion is, depending on the movement of an object, the Doppler effect can predict the speed or motion. Motion, and some of the main examples of motion are motion of a car, blood flowing through the vessels, and finally the rotation of the galaxy. And those all tie into motion because they're all moving. While they are moving, it causes frequencies. When stationary, the frequency waves seem lower, and when moving, it appears higher. And I would like to talk about two brief examples of motion. There are two different situations for the Doppler effect that we will investigate. The first is where the observer is moving. For example, you are moving in a car and passing by a stationary item. The second one, you are stationary and the source is moving past you. While the second is perhaps more common situation, the first is easier to analyze. You may think these two situations are the same. As it turns out, they are not. This means that you can also learn who is moving, the source of the observer. The first example is when you bob a boat up and down. If you're not moving and the boat bobs up and down with a certain frequency determined by the ocean waves coming in. However, imagine in the same boat you are moving, which will cause the boat to shake faster and create more frequencies. However, imagine you are going towards the waves while driving in the boat, which will cause the frequency waves to seem a lot lower pitched than you. And speaking more about frequencies, my partner Hung Vu will speak to you guys about it.
So other two factors would be the wave and frequency, which I will cover. So for the wave, the Doppler effect can be observed for any type of wave: water wave, sound wave, and light wave. We are more familiar with the sound wave because it's easy to imagine. As you can see in the picture of the ambulance, we can see the motion of the wave look like the graph of shine. Waves seem to compress or extend with moving source. And the distance between graphs is the wavelength. So as approaching ambulance to the observer, the wavelength is shorter. And as the receding ambulance, the observer wavelength will be longer. So basically the wavelength is different based on the source and the receiver. So we can come up with the formula of the wavelength, that the wavelength is equal to the speed of wave divided by frequency. We can call the red wavelength is when the source receding from the observer, and the blue wavelength is when the source moves toward the observer. And about frequency. Frequency is how often the wave travel to the observer. So as approaching the source of motion, the frequency would be high. Otherwise, the frequency will low when moving away from the source of motion. So for the information of the light wave, frequency is related to color, which I show you in here. So the lowest possible frequencies of visible light correspond to the red light. As we go to higher frequencies, we traverse the visible spectrum from red to yellow, green, blue, and violet. Light from a source moving toward the observer will be shifted toward higher frequency or equivalently toward the blue-violet end of the spectrum. So we can go to the formula of the frequency. So the formula of the frequency, we will find the observed frequency, which is the receiver. So C is the speed of wave, Vs is the velocity of the source, will be negative if it's moving toward the observer, and F0 is the emitted frequency of source. And now we will find the relationship between the wave and frequency. This is the sound wave. We have the police car with the siren light on, and as approaching the boy, you can see in the picture the small wave. He will have the small wavelength and high frequency. So the wavelength will smaller as approach the receiver, and as receding from a girl from picture, she will have the long wavelength and low frequency from her. So the next part will be application purpose, which my friend Michael will cover that part.
Okay, so apart from relating to motion and sound, the Doppler effect can also pertain to light as well. And an example of this can be seen with shooting stars and the frequencies of those, as Hung covered. And this frequency can be determined by the color of the star and the light that it's emitting as the waves are bouncing off of it. And high frequencies and short wavelengths create a blue light, while low frequencies and longer wavelengths can create a red light. And an example of this can be seen with the photo that I've provided here. As you can see, there's three different examples. The first example is of an object that's going away from the Earth. And because it is going away from the Earth, the waves, the frequencies of those waves are going to be a lot longer. And the wavelengths are also going to be a lot longer too. So smaller wavelengths and smaller frequencies. Now, as we transition to the right, we can see that the wavelengths here are actually getting smaller, more compressed, and the frequency is getting higher as well. So as it as it approaches the Earth, it's going to start getting a lot smaller and tighter, and that begins to shift from red to blue. That's why on the very end here, it's in the blue light spectrum, and then translating into purple the closer it gets, I guess. In the example in the middle, it's not necessarily blue yet, but it's transitioning from that yellow to or orange to yellow, and then yellow to green, yellow to blue. So it's making that transition from a red shift to a blue shift. And that can be used to actually determine the speed of objects and the overall expansion of the universe. And let's move on to the purpose of the Doppler effect and how it can be used. So this idea was actually first introduced by Edwin Hubble, and it was used to determine, as I said, the expansion of the universe. Red shift and blue shifts, they helped astronomers determine the speed and the velocity of objects as they're moving away or towards the Earth, and the direction as well. The velocity of these light-emitting objects could be worked out by them using the formulas that Hung provided, and they could determine things like the velocity, wavelength, frequency, things like that. And not only has the Doppler effect improved astronomical uses and things like that, but they've also spawned different applications in life. So we have different examples of it here. One can be seen with the meteorologists and their I guess, the knowledge on tornadoes and how quickly the tornadoes form and where they form and where they're going. The next one can be seen with handheld radar guns that police hold. So as a car is approaching them or leaving them, they can send out a ratio of waves, and depending on how quickly the waves return to them, they can determine how fast the car is going. So as we can see here, if the car is moving towards the gun, the frequency of the returning wave is actually higher. Usually it's going to be greater than the frequency that was originally shot out by the gun. So greater the speed of the car, the greater the frequency of the waves. And the last example that I'm going to provide to you guys is going to be about the Doppler echocardiogram. So this is basically what they use to determine, I guess, the ratio or the shape and the edges of the heart. So they send waves into the heart or into the human body, and they can adjust or view kind of the mechanics of a heart, how it's going. So the heart structure is going to be determined by the original echocardiogram. The Doppler echocardiogram is going to be used to figure out the speed of the waves, or the speed of the blood and the direction. So as the frequency is going to be transmitted into the heart, the waves are going to bounce off the blood cells, and that is what's going to be used to determine how fast they're going. And I provided a picture of that here with this example. You can see how as the blood is going towards the heart, which the heart is going to be in the center here, it's going to have a bluish tint to it, or a hue. And then as it's moving away, it's kind of translating into that red area, or like orange-red, things like that. So that's going to conclude it for me and our project. This is going to be the works cited, and you're going to get a link regarding our presentation so you can view that as well. Thank you.